Okay, so a couple of things. So there's a new homework set I just put up today. The first problem you should be able to do right now, and then we're going to be covering the ray analysis and imagery, holographic imagery next. And so the homework's not due until the 13th. So that'll be the last homework set. That'll be due before the midterm. So everything up through the imagery, I guess, will be on the midterm, which is on the 24th. So midterm is Thursday, the 24th of October. And oh yeah, and then also we have Lab 2. Now, Silvana's been kind of taking charge of these labs, and so she's kind of putting him more into the format that you had last time. The format I had prior to that was more of, here's a page of information, and there's the questions were buried in there. She likes to have the questions spelled out a little more clearly, which is probably a good idea anyway. So Lab 2, it's not, I don't have it posted yet, but I'll have it up there to either late today or tomorrow. So this will be next week. And then I will, just use the same lab groups that you used the last time, with the exception of, I think there were 2 students who ended up not taking it until that Friday. So if you guys can go on either the Monday groups or Tuesday groups. I think there was an AM and a PM on Monday, is that right? And then an AM on Tuesday. So that's coming up as well. Okay, so what we were doing, so we looked at several different hologram geometries. And so one of the main ones that we talked about was this Fourier transform geometry. And so we utilize in that this fundamental idea that, placing an object in the front focal plane here allowed us to get in the back focal plane an exact Fourier transform, which was something that we derived, or you probably have seen it in some of your other classes, or it's in Goodman's book in chapter 5 if you want to refresh yourself on that as well. And so here, again, we place the film in this back focal plane, and here there's an aperture essentially, and then we have displaced a little hole down here, right? And by illuminating that, what we end up doing then is forming the spatial frequency distribution here on axis at the film plane, and this point source basically out here gives us, again, so here we have a point, and we're going to end up with a kind of a plane wave coming out there. We could also have come in again with the most often it's done this way, where we just come in off axis here with a plane wave. Either way, we can end up forming this Fourier transform hologram. And then, going forward with it, we place this in the front focal plane of another lens. It may or may not be the same. If it's not the same, then we may get some scaling issues. Or scaling effects that we may want to take advantage of. For instance, if we're using this for a holographic data storage system, we may actually want to do some scaling, because the pixels that we would have on the writing instrument, like a spatial light modulator, might be different than the pixels on the camera that we'd be trying to register these pixels onto. So there we may actually want to introduce a different magnification through having a different focal length lens. But we could get, one-to-one imagery by doing having the same lens with the same lens characteristics, and then we would reconstruct, as we saw here, illuminating this then, well, actually, what we did was to illuminate this on axis like this, right? If we illuminated it off axis, we would then get, kind of an image here formed back in the center. If we illuminate it this way, we would end up getting, this is actually the way it's normally done, by the way, is we would end up getting several components. We'd get that delta function from the zero order. We get this one from A, autocorrelated with A, and then we would get, a real, say, not a real image, but the O and then O star being generated on either side of this center axis. Okay, so that was our, and these would be located like B away from the axis here and there. Okay, so again in the focal plane like that. All right. So that was the main type. We looked at that lensless Fourier transform hologram. That one kind of lensless. We didn't use a lens in the construction phase because there we would end up getting this spherical wave coming out. We eliminate that. We allow this to propagate, so we end up getting like a spherical wave which looks like a lens, and then that lens has its own quadratic phase factor characteristic, and then it ends up dropping out during the reconstruction phase. We still needed a lens in the reconstruction phase for that. We then had another geometry which is quite useful actually, and that is we have the object here, and we'll come back to this in a couple of lectures from now. And we place that in a front imaging plane, say D1 out here, and then we end up forming an image at D2. So we're not using the front focal plane and back, we're using the imaging conjugate planes here, and so we have the image formed there. And then what we do is we place the film in that image plane, all right? And so now the image that is being projected kind of straddles the film plane, and we expose that again with a reference beam, say for instance an off-axis reference beam like so, and this is called an image plane hologram. Again, it's a very useful geometry for display type holograms, transmission holograms. If we want to reconstruct it, say with an LED, this might be a very advantageous geometry to use, because as we will derive, the chromatic aberrations that we end up with are a function of this, say, this object depth or this image depth that we would have in the image plane. Okay, the image depth or the distance away from this hologram plane will affect the overall aberrations. You end up getting kind of an amplification of aberrations the farther away you go from the hologram plane itself. So by straddling the plane of the hologram here with that image, that kind of minimizes the extent or the distance of that object field that will be away from the plane of the hologram. And so by that, you're able to minimize kind of chromatic aberrations that we'll end up with. Which can be rather severe, as we'll see. Okay, so those were kind of the geometries that we talked about. There was one more that's kind of interesting and useful, and this one is referred to as a lensless Fraunhofer hologram. And this has some, again, some interesting properties associated with it. And it has seen a number of applications in the past. And now with the advent of digital holography, and kind of the resurgence in kind of in-plane or inline holography, it's getting more traction again. So let's look at this here briefly. So here we have our axis, and we place our object now is out here at some distance z0 away from the hologram recording plane. So here's the film, and this is the object plane that we have, which may have coordinates x1 and y1, and here we have x2 and y2. All right, so now as you recall, for being in the far field or Fraunhofer region, we have the condition that we need x1 squared plus y1 squared, the maximum value for the extent here in the object plane over the wavelength. This has to be much less than this distance that we're propagating it to. All right, so this is the far field condition. For the diffraction being categorized into that domain. And again, here's the object that we have. So one way we can reach this, all right, is to make x1 and y1 small. Okay, so we keep so our object has say x1 max is small relative to z0. Okay. All right. So again, so that allows us to be in the far field, and if we are in the far field, and again, so we illuminate this. So we're now going to illuminate this here, like so, and so we'll get some scattering off this, which will the scattering from that object now is going to give us the far field pattern out here on that hologram plane. And instead of blocking this as we did in the last time and putting a hole there, we'll just allow this to be transparent. So this field comes through as well. And so we get a inline reference wave illuminating the film plane. All right. So that's the situation that we have. So now, again, so with this, we can say, that we have the far field or the Fourier transform really of this object distribution. So if we have O of x1, y1 out here, in the Fourier transform plane, we're going to get the Fourier transform of that fx as the primary functional field, which again is just the Fourier transform of that O of x1, y1. All right, and again, this fx is now x2 over lambda z0, and fy equals y2 over lambda z0. All right, and so that's just the Fourier transform. The whole field that we have, the u sub 0 of x2, y2, is has in it this O, but we also have some other terms. So we have constant here over j lambda z0, and we have this quadratic phase factor exponential of j pi over lambda z0 times x2 squared plus y2 squared. The integration, again, in that Fourier transform was over x1, y1, the object plane. And so we have that times this O of fx, fy, all right? So again, so this is a quadratic phase factor, as you can see. And so that's multiplied by the Fourier transform of our object function. Now, again, so one of the areas where this is quite useful is in microscopy, all right? And so in that, in microscopy, you know, so we may be looking at like something like blood cells or something that are very small. Average blood cell is typically on the order of, you know, 5 to 7 microns, somewhere in that range. So if we go out here, you know, even centimeters or so, we could still be in the far field from that object. So in considering that, the objects then that we would have, this O of fx, fy, again, so this in the limit here is going to look like something like the Fourier transform of a delta function of x1, y1. So this then goes to 1, all right? And so, again, so this here is basically can go to 1 when we have very small particles, aerosol particles or blood cell particles. Actually, when I first, you know, learned about this, I did a master's degree at Rochester way about, I hate to say how long ago, 40 years ago. But anyway, there was a blood cell automated cytology system that was made. Brian Thompson was active in doing that. And he came up with this system for doing blood cell sorting based on looking at the diffraction patterns and recording them in the hologram. Okay, now, so you record these sort of far field patterns that you have in the hologram, and now what it looks like really is what you're recording now is a wave that basically has kind of like a built-in lens in it, right? Because this quadratic phase factor looks just like light coming from a point source. So basically you have, you know, the hologram has in it its own focusing element, which was set up by the object field, by these object scatterers. So it's kind of cool because you can now just move it around and always see an image of that object. So in the reconstruction phase, what we would do then to get this the intensity in your reconstruction, or I'm sorry, first during the construction, we'll get to the reconstruction, but during the construction we have now I of x2, y2. So this is going to look like our plane wave. So if we have a plane wave propagating in the plus z direction, minus j kz plus this u sub O field that we have here, all right? That's what's being recorded on the film plane. And so this then gives us our usual terms. We have 1 plus u0, u0 star, since these are unit amplitude plane waves. And then we have a e to the j kz u0 and e to the minus j kz u0 star. So what we can do then is, if we reconstruct this with a illuminate it with the conjugate, all right, so here we would illuminate this with e to the j kz times this I of x2 y2. Notice here, you know, we're going to end up getting the conjugate beam, and so that reconstruction again would look something like this, where here's the film that we have, and here's our conjugate beam here going in a negative z direction. And this then would focus the conjugate object field down to an image, a real image, all right? So now if you were to look at this, the other images, they would form, one would form a virtual image, would have some field out here, and there would also be this reference field, but the fact that this is being focused would increase the contrast of it, so you can actually see these images here with a microscope when you actually reconstruct it. So the idea here then is if you have this, these objects which may in fact be actually moving, you can expose this with a pulsed laser, get the object field illuminated and have your reference field. And that would kind of capture the motion, provided it's not, real fast. You would capture it, and then you can look at it at your leisure later on. So this is the same idea now, which is being used in a lot of digital holography techniques for doing microscopy. Okay. So again, that's the kind of the other another geometry that I wanted to let you know about. The interesting fact again is that you actually end up using this idea of having this quadratic phase factor recorded with the object field, and then you have your own built-in lens for the reconstruction process in that process. Okay. All right. Okay. So now we're moving on to another topic. All right, and this is going to be a kind of one of the major topics for the class. And in this, we're going to look at the imagery or image analysis of holographic elements. All right. So remember, early on, I said that there's really two different things that we have to pay attention to in holography. If we were doing refractive and reflective elements, this is pretty much all we would have to worry about, right? If we were doing analysis, then we can go on, Zemax or Code 5 or whatever, and do our image analysis and really come up with various designs for the system. However, because of the fact that the hologram is not a refractive but a diffractive, we're also going to have to worry about the diffraction efficiency. So this is one of the two major parts of evaluating holographic elements, or I'll be talking about HOEs here, okay, HOEs, and again, these are holographic optical elements. And so, again, a very simple holographic optical element is a lens, which, again, you'll be fabricating in Lab 2 next week. And so there, for instance, you can have a point source recorded with a plane wave, like that. And then during the reconstruction, again, what we might want to know is if we're going to use this actually as a lens, here we would illuminate it, say, with the conjugate reference field, and then generate a real point out here. That would be our O star, if that were R and O out there. All right. So what we're going to evaluate now are the imaging properties, sort of the ray analysis, and also some of the other features of this image process. And these, again, so there's a variety of applications for holographic optical elements, such as head-up displays, which have been used in aircraft, especially fighter aircraft, for probably the last 30 years or so. They're also starting to be used in some vehicles, terrestrial vehicles, cars, and so forth. And there's also point-of-sale scanners that are so commonly used in your checkout at stores, and a variety of these have holographic optical elements. And then UPS, for instance, when they have these big boxes and so forth, they're looking for that barcode. And some friends of mine, I worked for a while at IBM research in Almaden, and Harold Werlich was one of the guys, and Glenn Sincerbox. They developed a point-of-sale scanner, and this other guy, Richard Rawlinson, from another small company, and they made a ton of money on that. They sold it to UPS, and because they were able to sort, find where these barcode scanners are, but you had to have decent resolution for that. Okay, so one advantage there is you can use a laser. Okay, and so they didn't have to worry too much about chromatic aberrations. The other thing, though, too, is that if you were to do that same problem, if you needed a large optical system with conventional lenses, it would get kind of unwieldy, making very large lenses for that system. They have a lot of rotating components in some of those ones that are used in supermarkets because those are much smaller. But if you have a large system, having a holographic element that you can make in film and kind of copy is a much cheaper way to go. So it's much more cost-effective to use holograms in a number of applications. Okay, so let's look at image analysis, and there's a couple of different ways that we can analyze holograms. The first one we'll look at is an exact ray tracing method. This is extremely useful for a lot of portrayals of what the hologram will do, and this will give us a number of spot diagrams and other things just like you would have in evaluating conventional lenses and so forth. Then what we'll do here is to set up a set of paraxial image relationships. As if you've studied some geometrical optics, you know that having the paraxial image characteristics is extremely useful in doing any sort of image analysis. It gives you the first order kind of characteristics of that imaging system and a basis for how to develop it into something more extensive. And finally, we'll look at some of the aberration characteristics or aberration analysis of holographic elements as well. So all of these, and these are, again, the aberration analysis is also based on the paraxial image relationships that will form. Okay, so let's get started, and let's look at first the exact ray tracing. And fortunately, again, I have this chapter of my book, Word Process, and I put it up online, so hopefully you'll be able to read my writing much better than some of the other stuff. I ended up getting trapped into writing another book that's due in November. So once I get done with that, I'll get back to word processing the notes for this class. But anyway. Okay, so let's look at this now. So here we'll start out the ray tracing analysis. That in this will assume that the hologram is formed initially. So we already have this grading that's kind of established, and in general, we'll have we can have a volume hologram, right? That looks something like this. And I say this, and I want to emphasize this because there's a very important point that I want you to carry away from the class, and we'll dwell on this in several times so that you do understand it. And so here we can describe that we have a kind of a normal direction to this hologram, and then there's also a tangential direction along the surface of the hologram. Now, most of the time this will be just a planar surface. However, another nice thing about holography, and this has been used a number of times in the past, is the hologram itself can be deposited on a curved surface, like a helmet. And so now you can have a holographic element which is not on a plane. So we will go through the steps in taking this just from planar to curved, so that you can do ray tracing on any type of surface. All right. So again, this is something that comes up, and so it's quite useful and necessary to know. All right. So here we'll have a ray coming in. This is again the normal direction out here. And so we're going to have a reconstruction ray coming in. And I'm going to use the notation again. So we'll have O for the object, R for the reference beam, and we'll have P is going to be used for the reconstruction beam, and I is for the image. So that's a little key for all the subscripts here. But anyhow, we're going to have a propagation vector, say, if we're doing reconstruction, then we have K sub P. And again, this diffracts, and so we can get, say, maybe we'd have the 0 order. So we'd have a K0. We may have a +1 order, K +1, and K -1. So we can also have various orders that we'll designate as Q. So these are the diffraction orders. But generally, we're going to take like the +1 order, keep things simple. All right. So in looking at this too, we have a volumetric period. That's the distance between those fringe planes here. So this is the fringe plane in that hologram. We have of course, the K vector. The volumetric K vector is like so. But we also have the surface period. Bless you. And so we have along this surface, we're going to have a different period, lambda sub t, cap lambda sub t, which again is along that tangential direction. All right, so we can go back and use something that we derived earlier, and that is the grading equation. All right, and so that is then we're going to have, say, the sine of theta p for the reconstruction beam, and again, lambda 2 is going to be the reconstruction wavelength. And of course, lambda 1 will be the construction wavelength for this process. And then we have, again, just using our grading equation, sine of theta q for different orders over lambda 2. This is going to be equal to the order q over lambda sub t. All right. Okay. So if we can kind of play with this grading equation a little bit. Remember, this we can also say now, by looking at the components of our K vector closure, we can also say that we have Kxp along the x or the tangential direction. Say if x is along this tangential direction, then we can have Kxp minus Kxi is equal to Qkx, the x component, or that's equal to 2 pi over lambda 2 times this sine theta p minus 2 pi over lambda 2 sine of theta q is equal to q 2 pi over the cap lambda t for the tangential grading period. Okay. All right. So so looking at that and looking at our coordinates that we have, or our directions that we have there, we can then simply say that this is kp, the full vector, minus, this is going to be, although this is saying that we're in the q direction here, this q direction is really the image, right? This is the direction of the diffracted field. So we have ki, also a vector, the tangential component of that, and that's equal to q, k, volume vector dotted with t, the tangential coordinate. Okay. All right, now remember we had mentioned as well, or discussed this, the k-vector closure condition. So here for our full vector we have that k is equal to, say, kr minus ko, and so that's equal to, again, 2 pi over lambda 1. All right, this is the construction of that same grading vector that we have here, is formed by the, again, the overlap of a reference and object field, or beam. And this is equal to, again, 2 pi over lambda 1. And here we have some unit vectors, assuming n equals 1, kr minus ko. And so these are some unit vectors for that system. All right. So now, if we look at our relation that we have here, if we bring this over on this side and sub in what we have here, we end up with 2 pi over lambda 2 times kp minus ki, all right, the unit vectors, minus q, but so we will, at this point, we'll let q equal 1. We'll only talk about the first diffraction order. We can bring it in later if we need to. And again, so we're combining these two, and this has the construction in it. So we have 2 pi over lambda 1 during the construction phase times kr minus ko unit vectors. Okay, and all of that is times or dotted with t, the tangential component. And so that relation then is equal to 0. Okay, so notice what we have here. So we have, in general, we have something that looks like this, where we have a vector dotted with a tangential vector, and that's equal to 0. So what this here must be what? Okay, must be a normal vector, right? So this must be in the normal direction. So that's good. So we can also say then that from vector calculus, playing with that a little bit, that if we take the cross product of a vector, in this case a normal vector, with another vector which may be scaled but in the same direction, that also is equal to 0. Okay? So we can then take this term that we have inside of this parent here and rewrite it in the following way. We have two wavelengths, lambda 1 over lambda 2 n cross kp minus ki is equal to n, and again we could place q there if we want to, and set it equal to 1, carry it a little further if we wish here, n cross kr minus ko. All right. Okay, so we now have this vector relationship, and again this form here will be useful if we're looking at an arbitrary surface. But for now, let's make it a little simpler. And so let's have n equal to the z direction. And so then we can just rewrite this as lambda 1 over lambda 2, unit vector in a z direction, kp minus ki equals z kr or cross kr minus ko. All of those being unit vectors. Okay, so at this point, so we have this relationship. So all we've been doing is playing around with the grading equation, really, and going back into the full generalization in the form of k-vector closure to see how it relates. Okay, so now let's do something else. So we have all of these unit vectors, and there's some useful relationships that we can use if we look at those, consider those unit vectors to be direction cosines. Okay, another thing from our mathematical physics class or whatever. So direction cosines are nice because they specify directions relative to the different axes that we may have. So if here we have an x, y, and z axis, and let's say we have one of these unit vectors. So we'll just call it k. So we have that unit vector looking like that. All right, and so our direction cosines tell us that we can break down that unit vector into different components that lie along the x, y, and z direction. All right, and so what we have is relative to the x-axis, we have an angle alpha, and relative to the y-axis, we have here an angle beta, and relative to the z-axis, we have an angle gamma. So these are in 2 dimensions, so they're not in that plane, but they're actually, wherever you have this vector, doesn't matter where it is, you can place a value of this beta that goes directly to that vector. All right, and so what the direction cosines are cosines of these 3-dimensional angles that we have. So here, for instance, we may have a projection that goes parallel to this here, so it's going to go something like that. And so here we have L, okay, and so L is equal to the cosine of alpha, and then we have M, which is again going to be the cosine of beta. So here is M, cosine of beta, and of course the z component is going to be along the z direction, that's n. So we have L, M, and n, cosine alpha, cosine beta, cosine gamma. And the nice thing about this is we also have that cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma equals 1, or L squared plus m squared plus n squared equals 1. So it turns out the direction cosines are going to be very useful in talking about these ray trajectories. These vectors are nice, but if we really want to do the calculation, it's nice to break it down into something relative to coordinate system that we can reference ourselves to. Okay, and we can find these values quite simply in the following way, and this simply in the sense that this is a way which naturally will use, a natural way that we'll use in the holographic description is by different points on different planes. So here if we have a point, say x1, y1, z1, out here, and we have another point here, x2, y2, z2. So this difference here is z2 minus z1. We can get the direction cosine, and this is r12. We get the direction cosine in the following way. For instance, cosine of alpha is just equal to x2 down here minus x1 divided by this distance r12, and that r12 is equal to square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, which is also under that radical. Okay, so again, so we have a simple way to get these values from the characteristics that are used, or the parameters that are used, say, in forming the hologram. You know, because we normally talk about point sources or points on the hologram and so forth. So this is the natural way that will flow from describing the hologram. Okay. All right. So now let's look at this relationship that we have up here again. All right. So notice that we have this for any for any of our unit vectors. All right. So we have kp, we have ki. This is what we're trying to get. Okay. This is what we need. And we have kr, and we have ko. All right. So the relationship between all of these are given by that. All right. And as you can see from this diagram, k now has, you know, an x component, which is L, a y component, which is m, and a z component, which is n. All right. So we can go back now and use this vector relationship with the direction cosines in it. So here we have, for instance, for example, if we have this cross product, the unit vector z, which was our normal vector to the surface, dotted with or crossed with kj, where j again is equal to p, I, r, or o, any of those. This is going to look something like, you know, doing our cross product x, y, and z. Z is 0, 0, 1, and then we have cosine of alpha j, cosine of beta j, cosine of gamma j. All right, so again, we just have our little matrix set up for that. Again, so this we can substitute the L, M, and Nj values. And so this we do the multiplication, so we have x times this minus that, you know, minus y times that minus that, and so forth. So we end up with something that looks like minus mj in the x direction, minus a minus lj in the y direction, and then a 0 in the z direction. Okay, when we do that cross, since we're crossing it with z, it's got to be normal, or the component that's along that direction falls out. So we go through this, right? So we're going to have x components and y components for each of these, p, r, and o, and I. All right, and so if we equate equating the y components from this process, we end up with the following, that we have, so notice using the y components, we end up with the L's, all right, which are the x projections. So we have 2 pi over lambda 2, LP minus LI, minus 2 pi over lambda 1, LR minus LO is equal to 0. Or we can just say, LP minus Li is equal to lambda 2 over lambda 1 Lr minus Lo. All right? And then similarly, equating the x components, we end up getting the m values. So here we get mp minus mi, kind of the same thing, equals, and if we wanted to carry the q, we would have the q in here as well, just in case you're wondering where that went. Lambda 2 over lambda 1 mr minus mo. And now for the z component, we use the this relationship for consistency. We're going to use that relationship because here, for the direction cosines, we can't specify another value for n. It has to be consistent with the L and M that we have. All right, so we need to use this relationship here. That gives us, again, it has a unit vector, so that gives us the magnitude of 1. All right, and so for the n components, n sub I is just equal to 1 minus L sub I squared minus M sub I squared, the square root of that. And notice we can solve for Li and Mi from these relationships here. Okay, so what we have, again, in this is we have a value of alpha, we have a value of beta, and we have a value for gamma in the actual angles. All right, so these relationships that we just derived, these are kind of similar to, these are the directional change parameter in the ray trace, or the directional change that's specified in the ray trace. Okay, so this is similar to the, the refraction Snell's law. And what it really is a glorified grading equation in 3 dimensions, okay? Because that's really what we derived. We went through and we got that k-vector closure, and then we took the tangential component. So let me emphasize again what we have done in this derivation that we have here. The important component for determining the ray directions is this guy right here, that tangential grading or period component. This determines the direction of the diffracted beam. Okay? Very important point. And the reason it determines the direction of the diffracted beam is because that's at the boundary, that's at the interface, right? So what you have there is a boundary matching, electromagnetic boundary matching condition. Just like Snell's law is the same thing. Snell's law comes out of electromagnetic boundary matching condition at 2 refractive surfaces, right? The kx component, right? Of you do that matching of n in n 2 pi over lambda in one and n 2 pi over lambda in the other material, and you end up with Snell's law. Okay, this is the same thing, except it's based on the grading equation and the grading relation, the phase matching that we originally established where the grading equation came from. Okay, so later we'll see that this volumetric period, that is going to determine the fraction efficiency of the grading and how well we match that. Okay, so again, these are 2 fairly distinct characteristics revolving around the way in which we look at this, the periodic structure and where it lies in the overall scheme of the electromagnetics of the problem. Okay. All right, so just like in ray tracing, you have refraction, and then you have transfer, right? You have transfer between two planes. So this is part of the ray trace solution. We still need the transfer relation, though, right? So here, so this is the directional change, and now we need the ray I guess we'll properly would call it the ray transfer. So that's not too hard to do, but there's a little trick that we have to incorporate in order to get that. All right, so what we're faced with here, so here is our hologram plane. And in ray tracing, we somehow have to know where we're going to do the image analysis. So in your normal ray trace analysis, you usually use the paraxial image plane, right, to kind of put everything and evaluate your image there. And then you may shift things around from that, but you use that as a starting point. Later we'll derive what the paraxial image plane is for the hologram. But for now, all we need to know is that we will calculate what that image evaluation plane is. So that's z sub I, and so this is going to be known in some way. So we put another plane out here, and this is where we're going to look at the spot diagram or the image that we're going to form. So again, here's the image plane. And so we have, again, so we have a y and an x and a y and an x. And so in order for us to do the ray analysis, we may have a fairly complicated grating that we've recorded. It could be a spherical wave that we were recording in combination with some sort of reference field. It could be an aspheric field that we're recording, or it could be some arbitrary object field. All right. So regardless of what it is, we can always break it down into a kind of a localized plane wave, and it has some sort of grating vector associated with it. So we have this localized planar, not plane wave, but planar grating. And again, if we look at our frequency spectrum, we can eventually come down to some small area. There's some criteria that are used in determining how small that region has to be. But this is going to be very useful because just like you have in refractive and reflective ray tracing, when you do your spot diagram, there's kind of a rastering of that aperture, and there's little points where rays are projected through, and you do these Snell law or reflection law calculations over and over and over again. We're going to do the same thing here, except we're going to raster, but now we're going to use our directional change relationships that we just derived at each of those different localized planar grating locations throughout the aperture. So it's the same thing. We're going to raster that aperture. We calculate a little localized planar grating there. We do a change in the direction, and that change in direction is for our reconstruction ray, which may come, say, from a point here, P. This is again, that's our reconstruction ray. And this grating that we have here is set up by, say, a reference and an object wave, which again corresponded to this over here, where we have this unit vector KR and KO. Those are in those two directions that we have there, going to that particular point. All right. Okay. All right. So this is a point on the hologram, H of, we'll call that XH, YH, and we'll let Z equal 0 there, since we can reference it. So this is YH and XH coordinates there. And so the ray comes in, and then it diffracts out over here, over to some value. Okay. So something else we could do, though, is we can just project parallel to our axis here, although my drawing may not look too much like that. So we have a diffracted ray coming from our localized planar grating, and we have just a projection here. So this projection on the x and y axis has values of just xh, yh, and now it has zi for the z coordinate. And this is our image point, right? So this is going to be xi, yi, and zi. So we have zi, but we don't know xi and yi yet, right? But we do know what the angle is here. And we also know, again, so we could calculate this distance. This is ri, the distance value. That's just a scalar. And then relative to the z-axis, like we just moved that z-axis up there, we have gamma I, right? So we have gamma I, and we notice that we have gamma I. Gamma I is right there. Comes out of that. So this is the little trick I was telling you about. So here again, so we have, this is along the z-axis, and we have, here is Ri, here's gamma I, and so if we project this down, that's equal to Ni, which is, Ni is equal to the cosine of gamma I, but that's equal to, the cosine is just equal to Zi over Ri. And we know Zi, and we also, and so now all we need to find is Ri, right? We have Ni, we have Zi, and now we can get Ri. So Ri is just going to be equal to xi minus xh squared plus yi minus yh squared plus zi squared, all of that to the 1/2. And xi is equal to ri times li plus xh, and yi is equal to ri times mi plus yh. So these are the transfer relations, all right? So we have, again, so we have the value for Ni, we have the value for Zi, we can get Ri, and then that gives us the values for Xi and Yi, okay? So we can write, so we now have our ray trace, all right? And so kind of an algorithm, just to kind of recap here, ray trace algorithm, which, by the way, I asked you to write a little program like in MATLAB or something in homework 3 to actually run through this. So the first thing that we'll do, as I mentioned, is we divide the... Yeah, let me make that wee smaller. There we go. So the first thing that we do is, as I mentioned, we have the hologram plane out here. And so you want to divide this up into a bunch of little pixels. All right, and then we're going to do that local plane wave analysis or plane grading analysis at each of these. And because the construction and reconstruction conditions are going to change for each of those. So you need to calculate, this point here is going to be known, this point's known, that point's known, and you're going to change these points. And so with that, you can use this relationship here to calculate what those direction cosines are, right? So it's pretty straightforward, I think. So what we do first is, again, divide the hologram aperture into pixels. And then we're going to use that local or localized planar grading analysis. All right, and then so the next step then is for each of those different points, we're going to compute the direction cosines for O, R, and P, the reconstruction ray, the construction and then the reconstruction ray, using, again, that relationship that I gave. And then the next step is you do the, calculate the new direction for the image ray direction, compute the image ray direction, which is the Li, Mi, Ni, using, again, this set of relationships that we just calculated. And then the next step is to determine this Ri, which is this distance here, which we get from that kind of definition almost. So we have Ri, again, this is equal to Zi over Ni, that n direction cosine relative to the z-axis. And then we apply the transfer relationship or relationships to find the image interception points, or the image points on the evaluation plane at Zi that we have. And then you just repeat this for all your points in the hologram plane here. Okay, so it sounds worse than it is. It's actually pretty simple to set up. And in my notes, I actually give a, so here, I mean, this is a basic, program that you can use for doing that. So it's pretty straightforward. And again, there's some examples in my notes that you can use for a model. Although it would be good. I'm sure you have your own ways of doing it. So it would be good for you to step through that. Okay, and I do ask you to do that in the homework set. Okay, so that is our first method of analysis. Now, the thing that you'd like to know, though, is what's a good plane here, Zi, to use? What's a good evaluation plane that's a good starting point for the image analysis plane? So the next thing that we'll do is develop the paraxial image relationships for the hologram, all right? And for this, we're going to look at the kind of the phase, like we do in all holography. What we're really doing is looking at the phase difference between, an object and a reference field, and then we look at the phase matching condition when we do the reconstruction. So the phase is naturally very important. So what we'll base the paraxial image relationships are are on phase matching relations. All right. So I'll get a short start here before the end of the period. But here we have our, one of our planes here that we're talking about. So for instance, this could be, say, say an object plane that we might have, and then here, we're going to form a phase difference out here on the hologram plane. And so that kind of defines our object field plane. And so we have some point out here. This is located some distance z away. And so what we really want to know is what is the phase of that object wave, for instance, at some other point P out here, which may be at x, y, and z. And this might be some object point. We'll call that S of x1, y1, and for z, we'll set z equal to 0 on the object plane. So here we have z equals 0, and here we have z equals z. Okay, so if we want to know what the phase is, we can calculate that by taking the full path length there. The phase is going to be equal to 2 pi over, say, lambda times this distance that we have, SP. Okay, but if we take that distance, okay, we end up with a really large phase. All right, so oftentimes what's done is to kind of normalize the phase or reference the phase more exactly to another phase which goes from that point to the origin of our evaluation plane, the hologram plane here in this case. So here we have another point, P0, at the origin, which has coordinates 0, 0, and z. So the phase that we're actually going to take, for deriving these paraxial relationships are referenced to a similar path length phase which goes from that same point to the origin of this hologram axis or hologram plane. Okay, so we will pick that up next time, and if you have any questions for Thiago, he's sitting there, and we'll see you guys on Thursday.